Welcome, everyone. Thanks for joining in on this session on scaling Gloo Mesh to achieve performance and reliability at scale in production. So today I'm going to talk about how can you scale your Istio service mesh in a single cluster and multi-cluster environment, some of the challenges you might face, and how Gloo Mesh is fundamentally architected and designed to solve those challenges and meet the requirements for production at scale. So let me start off with some introductions. I'm Neeraj Poddar. I'm head of engineering here at Solo. I have been a long time Istio maintainer, have been working group leads for several working groups like networking and product security working group. I'm a former steering committee member and currently on Istio TOC. So let's go over today's agenda. First, I'm going to talk about what scaling means for Istio service mesh in a single cluster environment. Then talk about multi-cluster scale challenges, but focus on the requirements that most of our customers have for multi-cluster mesh, what architecture and what solutions Istio provides, and then some of the challenges you might face with it. Then I'm going to talk about the Gloo Mesh solution, how our architecture is built to handle those challenges, and then move on to some of the amazing enhancements we have made in the Gloo Mesh version 2.0 product. I'm going to conclude this session by making some recommendations for running Gloo Mesh effectively at scale in production. So let's get started. So first off, let's look at the Istio architecture, and so that we can understand what scaling means here. So Istio primarily is composed of two components, the data plane and the control plane. Our data plane is comprised of sidecar proxies. These proxies are envoy proxies, which are deployed in a sidecar proxy architecture. By sidecar proxy architecture, I mean these are injected in the same pod as the application container, and we add some IP table magic to make sure all the traffic from the application container is injected and sent to the envoy proxy. Similarly, all the traffic coming into the application pod is intercepted and routed through the proxy. Because these are in the same pod, from an outside point of view, they look as one logical entity because they share the same networking namespace. So basically, after all the data injection has been done, what it means is when app A talks to app B, the request will go through the envoy on the app A's pod, and then it will be intercepted by the envoy on app B. And then similarly, the response will go through the envoys on the reverse direction. So that's the data plane component. The second component is the control plane, which is called Istio Discovery, or in short, it's called Istio-D. It's responsible for looking at your platform configuration. So for example, if you're running in Kubernetes, it will look at all the services you have and the user-provided mesh configuration and translate that to all the data plane proxies. So basically, Istio-D is an abstraction layer that lets the operators configure Istio in the language of the platform, and basically in Kubernetes, and then hides away all the complexity of the envoy configuration. At the same time, Istio-D is responsible for managing the identity and certificates for the envoy proxies themselves if you're using and turning on the mutual TLS capability. Another important aspect of Istio service mesh is the telemetry that the envoy proxies surface when the traffic is flowing through them. All that telemetry, all the metrics specifically can be gathered by the Prometheus, by running Prometheus in your cluster, which for me is also part of the control plane, as getting the visibility is an important aspect of the service mesh. So next, let's look at what scaling means, right? We'll talk in terms of each component. So for data plane, since the envoy proxies are injected in the pod as sidecars, when you scale out your pod using Kubernetes primitives, the data plane scales with it. So that's very beneficial. So for example, if you have 2 replicas of app A and now 3 replicas of app B, you have in total 5 envoy proxies running, matching the 5 instances of your application. So this scaling is very beneficial. You don't have to do extra work. You automatically get it by just using the Kubernetes primitives of deployments or daemons, whatever you have. So that's great. The second scaling aspect is how do you scale the control plane? So Istio allows you to run multiple instances of Istio-D. So the primary benefit is when you have multiple instances, the proxies that connect to the Istio control plane for getting getting the configuration, it gets load balanced to those instances. So for example, here, the app A sidecar's proxy can go to the Istio-D on the left, and then the app B might go to the Istio-D on the right. This is great in terms of dividing the load for the connections that are being handled by one instance. At the same time, there's a limitation here that all the Istio-D instances end up looking at the entire state of your Kubernetes cluster, of your platform, and the configuration, and compute the output results for all the envoys. There's no fundamental sharding at how the services and the configuration will be divided. So this leads to limitations around both the Istio-D instances will more or less consume the same amount of CPU and RAM when they are working at scale and looking at large number of services, large number of configurations. Right. So you get the benefit of the envoy proxies getting load balanced for trying to get the connection, but the limitation is you don't really have some efficient sharding here, right? So that's what is summarized in the slide. Another aspect of this scaling is in Istio by default, all the proxies are configured with the entire state of the system. That means if you have large number of services, each of the proxies will have connectivity information, and which means clusters and endpoints associated with all your services. That can be reduced if you are configuring sidecar resources, but Istio cannot automatically do that. And it's very tedious and very onerous to configure the sidecar resource as it's a very low-level resource, and it's not intuitive for the users who are trying to configure traffic behavior. So now we're going to talk about what Gloo Mesh provides in terms of its solution and architecture, and then how we are solving some of these challenges, right? And how we can make the scaling better going from one cluster to multiple cluster, right? So when we talk to our customers, a majority of them have requirements for multi-cluster mesh, right? And that fundamentally stems from the fact that you might have reached the capacity for a single cluster in terms of number of services and resources you have. So you have to go to multiple clusters, or you have security requirements where you have different organizations, different BUs, which are fundamentally multi-tenanted. You need to isolate them and you have multiple clusters for that requirement. Or you want some reliability. So you want multiple clusters deployed so that if one is having issues, you can fail over to the other. Irrespective, for most of our large customers, multiple clusters is basically a requirement, right? So you need to have applications deployed in one cluster, which are able to communicate effectively to applications deployed in another cluster, all while preserving end-to-end identity. And that's what the first requirement for a multi-cluster mesh at scale is. You need to have inter-cluster traffic. You need to have seamless traffic that allows communication between applications, and they can be deployed across clusters. You preserve the identity for end-to-end, and you can have failover support. So if you're going across regions, you want to only failover when the instances of services in your own region are failing. So you have some cost optimization done there, right? You want fault tolerance between these clusters. What I mean by that is each cluster and mesh should be functioning independently. You don't want to have the mesh or the Kubernetes server on one cluster going down, affecting the functionality and the traffic behavior of other clusters. Essentially, many of the times the customers are moving to different clusters, like I said, for reliability. And if you have these dependencies, you lose that aspect of you lose that benefit from it. And lastly, we want services that are deployed in each cluster to have overlapping IP addresses. Basically, we don't want to have requirements around networking being flat. You want to make sure your clusters can be deployed across different clouds. You don't want to make any assumptions around how the topology of the clusters is. It might be simpler to come up with solutions when you have flat networking, or all the pods are reachable from different clusters directly. That's why we want to make sure the solution we come up from multi-cluster has these requirements met for the architecture in them, the architecture that we come up with. So for these requirements, if you take these requirements basically in Istio, this is the architecture that works for you. So Istio has a lot of different solutions when it comes to multi-cluster. But on these requirements, the architecture that works is you need to give Istio-Ds running in each of these clusters access to the Kubernetes server. And that's needed because Istio-Ds will automatically discover endpoints so that services from one cluster can transparently talk to another cluster. While this looks very attractive in terms of simplicity, there are some severe limitations of this architecture, right? So the main limitation from a security point of view that I've often seen customers mention is this cross-cluster Kubernetes API server access is a security it's a security violation in terms of isolation. You want to lock down access for Kubernetes API servers to a small group of services, probably which are living inside your own cluster. You don't want an actively running service outside the cluster which can reach into the Kubernetes API server. Secondly, since all the Istio-D instances are talking to each other's Kubernetes API servers, you're basically limited by the scalability of a single API server. Additionally, all the configuration overhead is basically on the users who are running this architecture. So you need to replicate the configuration across different clusters to make sure you have the same policy and the resources running across. So you get consistency only if you do this manual replication. At the same time, you need things like consistent naming. So you have to have the same review service named running in cluster 1 and running in cluster 2 to ensure you get load balancing across cluster for the review service. If you have some instances running in cluster 1 and some in cluster 2. The trust bootstrapping to ensure you can have mutual TLS for traffic across these clusters need to be bootstrapped manually. And then all the visibility aspects are basically left on you as a user to build up to ensure you can get understanding of when the traffic is leaving from one cluster to another. Are you having failures when that is happening, right? So you can have Prometheus instances deployed in each cluster, but then once the traffic goes from one cluster to the next, how do you actually get the metrics reported in a way so you can have a good connectivity graph? So these are the problems that the Gloo Mesh solution solves. So in Gloo Mesh, you have Istio running in each cluster. These Istio instances are independent. So for all intents and purposes, they're not aware of the Istio instances running in other clusters. What we do is we are adding an agent that runs in each cluster. This agent is responsible for looking at the Kubernetes services, looking at what Istio resources are running on this cluster, looking and discovering the various input objects and providing them to the management plane, which runs in one location. So basically, all the agents are going to discover these objects from each of these clusters, send them to the management plane, and then the management plane is responsible for taking all of the runtime information for various clusters, combine it with the user information for the Gloo Mesh custom resources, and then create Istio outputs by taking these inputs. So the Gloo Mesh management plane is doing this translation from your runtime state and from your Gloo resources and creating the snapshot, which is pushed down back for each cluster to the agent, and those agents are then creating the Istio resources. So then the Istio resources are created individually for each cluster. Then Istio-D is taking those Istio resources and converting them to the Envoy instances. Having this architecture fundamentally gives you better flexibility and scalability compared to the architecture where you have to have connectivity across each of the API servers, right? So if you look at this architecture, the main benefits that you're providing is we don't have the security issue of cross-cluster Kubernetes API server access, right? We have agent which is going to do the discovery and send the information out, and the same agent will do the application of the Kubernetes Istio resources on each cluster. So there's a nice security isolation boundary. We also give our users a higher level APIs, which are persona mapped, instead of lower level constructs, which you have to deal with when you're configuring Istio directly. It's more intuitive, it's more applicable to the persona that is configuring the system rather than all lower level networking APIs. Right? And the interesting thing here is Istio is powerful enough that it gives us the right primitives to build on and create high level use cases and high level management plane and products like Gloo Mesh, right? Additionally, we are automating the Istio configuration creation in each cluster and management. So you don't have to do that manually. You don't have to do the replication or whatever Istio config is needed. You can all drive it just by creating Gloo resources. We also provide automated trust bootstrapping and a single pane of glass for visibility. So what I'm going to do next is we're going to zoom in into the Istio in the Gloo Mesh architecture and actually show you how we provide each of these aspects, especially the last two, how we are doing the automated trust bootstrapping and how do you make sure we have visibility for traffic going across clusters. So this is what we call the Gloo Mesh relay architecture, right? So in Gloo Mesh, like I was saying, we have the agent, which is going to look at the Kubernetes API server, get all the information about the services and endpoints, send it securely over the management plane, which we call the enterprise networking pod. And the enterprise networking pod looks at the Gloo resources, combines it with the stuff agent has given, converts to the Istio resources, sends it back down to the agent, which applies it. So this fundamentally is very scalable because each of those clusters you can see will have the agent running. As the workload clusters scale, you will have each independent agents doing this work without any coordination between them. So whenever you see terminologies like relay architecture and relay in our documentation, this is basically the communication path we are referring to. So building on this, let's look at how Gloo Mesh handles trust. So in Gloo Mesh, there are multiple kinds of certificates. And depending on how you have configured it, we can automate some of it or all of it, right? So two primary certification, two primary certificate systems in Gloo Mesh are one that is being used for relay. That is for communication between the agent and the management plane for getting all the config back and forth. And then another certificate management system is the data path certificate system that will be used by Istio-D, and then all the workloads for securing traffic between them with MTLS. Right. So here, what I'm showing is one of the ways you can configure it. Right. So you can have one root CA that is going to be creating two intermediate CAs. And in this case, the intermediate CA will be used by the management cluster to create the relay server certificate, and then also to create the agent certificate. And then the intermediate Istio CA will be used for all the Istio-D signing certs, and from there creating the workload certs. So in this mode, you are going to have one root CA maybe for your organization, but then the intermediate CAs have Gloo delineation where they can be used for kind of control plane traffic between the agent and the management plane, and all the data plane where you have another CA system going on. In terms of management of these certificates, you have, again, a bunch of different options. This is one of the options that I like to show because this is most commonly what's used by our customers, right? So you can have the root CA configured so that it is provided externally. It's handled externally like a Vault or AWS certificate management system. So in that case, the root CA will be configured manually, right? You have to provide the root CA and the intermediate relay CAs and the Istio CAs to us in the management plane and the relay server certificate. But from there on, all the certificates will be automatically generated and rotated and managed by the Gloo management plane. So from there on, the agent certificate and the Istio certificate will be created by us. The Istio-D will look at those certificates that we have manually provisioned. From there, they will create the workload certificates. So this is like a hybrid mode in which some of the work for management is on the user, whereas the rest of the trust bootstrapping is uh, done by the Gloo Mesh management plane. Moving forward, let's look at what the observability primitives are and how we can have the single pane of glass in the Gloo Mesh product, right? So the enterprise agent that's running in each cluster is doing the relay work for getting the configuration up to the management plane and getting the Istio configuration down. At the same time, it also acts as a metrics and a log server. So what I mean by that, when you're running Gloo Mesh, we configure the sidecar proxies running in each pod to send the metrics and logs to the enterprise agent at a specific port where it is going to receive those metrics and logs and send them via mutual TLS again to the enterprise networking pod or the management plane where the management plane acts as a sink. Because these are running in each clusters, and we add specific labels or tags for traffic coming for each cluster. So basically what you end up having is all the metrics and logs for all your clusters are sent by agent to the networking pod running in the management plane. And then in the management plane, you will have Prometheus running, which can scrape this metric. And that can help us create visualization for traffic going from one cluster to another because we are not losing any of the context. You can have Prometheus running securely in one place where you can scale it up. And then you can have all the telemetry for all the clusters in one spot. Additionally, our dashboard has the visualizations to make sure you can actually look at the graph going from one cluster to the other. The dashboard itself coordinates with a bunch of different things. So the dashboard in the version 1.2 of the product is going to get the metrics from Prometheus. It also communicates the enterprise networking pod to get some intermediate objects. And then it communicates to the Kubernetes server where the enterprise networking pod has persisted some intermediate objects. It combines all of them together basically, and the UI gives you a holistic view of your configuration and the runtime state with all the graph and showing you the connectivity between services deployed across clusters. So now let's talk about what scaling means for Gloo Mesh even after this, right? So we have a fundamentally secure architecture where the agents are doing the work securely in each of the clusters, and then the information comes up to the management plane. But you can see we want to make sure we can scale out each of these components so that depending on the size of your cluster, none of them are having issues transporting data. None of them are actually acting as a choke point, right? So this is the first aspect of scaling Gloo Mesh. So you can scale out the Gloo Mesh agent into multiple replicas. So this is going to be supported in version 2.0. So in this case, what happens is we are running a leader election for the multiple instances in agent. Whichever instance is the leader is responsible for the relay architecture. So it is going to be responsible for sending the Kubernetes state and runtime information like services and Istio resources that are currently created, and then communicate to the networking agent pod, communicate to the enterprise networking pod in the management plane. But all the other instances which are not running in the leader mode are going to still be serving and acting as the metrics and log server. That means when you have multiple instances when you have a lot of different workloads running, they can connect to different agent to make sure you can get all the metrics and log exported to your networking, to the management plane, right? So this gives you the first level of scaling. So your relay is handled by the leader, and all the other instances are able to send the metrics and logs up. So if you are growing your applications in one cluster, this can still handle the load. But as you can imagine, just scaling the Gloo Mesh agent is not going to be enough, right? You can still be bottlenecked at the Gloo management plane. What we found in the version 1.2 was there were a lot of inefficiencies in translation that were actually linked to propagation delay at scale. And that propagation delay can sometimes, can get worse and worse as you add more configuration in your cluster, or you are adding more as you're adding more clusters and scaling out, right? So we wanted to address that in our new release. Additionally, an interesting aspect of the design we had in version 1.2 was the Gloo Mesh management plane, or the enterprise networking pod, was doing a lot of writes to the Kubernetes API server to persist intermediate state. Now that's beneficial in general because you can query the Kubernetes API server and get a lot of debug information. At the same time, it was causing a lot of issues in actually trying to scale that out when you are having a lot of clusters and a lot of data flowing through your system, configuration data flowing through your system. Another interesting thing was we only allowed the Gloo custom resources or API objects to be written to management cluster. You want to make sure you have redundancy, and you want to be able to write those objects in all the workload clusters, not be restricted to just the management cluster. And then the key thing was that was missing in our earlier architecture was there was no easy way to organize data in the dashboard or in our translation at scale. We didn't have a good unit to say, this is how we should be processing data. This is how we should be showing the data itself, because Kubernetes provides namespaces as a way to draw boundaries or create multi-tenancy. But often namespace is not enough. Many organizations are deploying applications across multiple namespaces, and for them, that is the tenancy boundary. Similarly, when you scale out to multiple clusters, you can have the applications deployed across different clusters that are logically one entity, but they will be across different clusters, across different namespaces. So we needed to come up with something better that gives our users a way to describe multi-tenancy in the way they are thinking, at the same time use that primitive to make sure we can better scale out our components, particularly the Gloo Mesh management plane, and then help the dashboard organize the data in that way. And that's what we did with Gloo Mesh 2.0. So we introduced the concept of workspaces. So workspaces are logical boundaries or containers, which gives you this benefit of multi-tenancy in regards of isolating your configuration and also isolating traffic between services that are part of workspaces or that you have imported, right? In Istio, multi-tenancy in general is very difficult, especially in terms of configuration. In Istio, it's very easy when you can have one Istio resource created in one namespace that can hijack traffic in another namespace, right? This is not saying that the Istio APIs are not capable of doing a lot of other things. It's just by design, because they are so powerful, they also have this limitation. So we wanted to create a logical boundary so that whatever Istio resources, whatever Gloo resources you create in that boundary will never affect outside that boundary unless you explicitly tell it to. And that's what a workspace is. Additionally, when you are creating a workspace, you have an option to say that all my services within the workspace can talk to each other. Whereas for anything outside the workspace, I will need to explicitly enable it one by one. Going further, because we wanted workspaces to span different namespaces, to be a construct that is constructed across clusters, we allowed our users in the APIs to inform us what your workspace should be composed of. So when you're creating a workspace, you can specify which namespaces from which clusters are part of this. And that's basically your application boundary, or that's the boundary that your team deals with. So you can see in this diagram, we are showing how workspaces are drawn, right? So the dotted blue lines are showing workspaces that are sometimes just spanning one cluster. The other workspaces are spanning two namespaces across different clusters. And the third one is actually composed of 4 clusters, right? And you can compose them however you want. And we have primitives in workspaces that allows you to export and import at various resolutions. So basically you can say I'm importing a particular workspace or a resource or service within that workspace that allows you to basically start consuming it. But without doing those imports and exports, you are basically in an isolated environment, and you will never affect anything from a security point of view, something that is in a different workspace. So this is basically summarizing the benefits you get out of it, right? So you have strong multi-tenancy guarantees for configuration and traffic flow. You can enable cross-cluster application deployments without naming restrictions. What I mean by that, you don't have to have consistent naming anymore. You can have different names, or you can have the same names in different workspaces because those are very well bounded. Additionally, we can automatically create the sidecar resources because we know your service dependencies as you have described in the workspace. Now we can reduce your memory and CPU consumption in Envoy for processing a lot of configuration. This is a big benefit at scale. Now, as part of this rework and creating this 2.0 product, we also are allowing Gloo Mesh resources to be treated in any cluster. And we have an efficient way of organizing data, using that organization for efficient translation and then scaling of the dashboard, because our whole new version 2.0 dashboard is geared towards showing you objects within these workspaces, whether it's showing you what resources and policies and services you have or your graph. They're all oriented around this workspace, and it makes it very easy to scale our backend systems and our front-end systems. So this is what, in summary, the 2.0 scaling looks like for Gloo Mesh, right? So we were already scaling the enterprise agent pods for multiple instances. Now, so with some of the restrictions and re-implementation, restrictions removed for early architecture and the re-implementation of logic with workspaces, we have capability to scale out enterprise networking pods, or it will be called, I think, the Gloo management pod in the new version, to multiple instances. So this is very interesting, right? So the multiple benefits you get out of it. So as the different enterprise agents across different clusters connect to the networking pods on the management plane, you get a reliable way of sharding your data. So as the leader in each cluster, as the leader agent in each cluster connects to one of the instances of the management plane pod, that management plane pod only needs to worry about the configuration for that particular cluster. It doesn't have to worry about cluster 2, for example, if the leader for cluster 1 connected to it. So this sharding is very useful, and it's automatic, because as the leader agent comes and picks up one of it connects to the networking pod, it is going to connect to one of them, right? It will automatically get load balanced. So that gives us a unit of division of work that helps us scale better. Similarly, the efficiencies we are getting because of better translation and reduced transport of objects between the agent and the management plane, we get better scaling there too, right? So the enhancements that we have made in Gloo Mesh 2.0, to summarize, you can scale out the management server pod, we get efficient sharding. We have reduced the number of intermediate objects that we are creating, more importantly, that we are persisting. That helps us make sure we can do translation quickly at scale. We are reducing the relay of objects to the point whatever is needed, those are the objects that are transported from each cluster. That saves some bandwidth and also churn time in terms of processing. So with these enhancements, I'm very excited and looking forward to what our customers can do in production to get better scale. I'll highly recommend that you scale out the agent pod and the management server pod on the management cluster. Make sure you have anti-affinity configured for control plane pods. So basically, all the different instances of the agent and the management server don't end up on the same node in case a node goes down. You want to have resource constraints on each of the control plane pods based on the load, which you should be monitoring and scaling them up or down depending on your consumption. You want to make sure you're bootstrapping your trust using your organization's root CA. This is very important because by default, the Gloo Mesh product will use a self-signed CA, which is great for demos, but for production use cases, you want to use your organization's CA. Now make sure you have enabled the metrics and access log service. By default, it's on, but if you have turned it off, you should understand once you have this system turned on, you will get a single pane of glass and all the metrics and logs will be aggregated in one place for you to visualize. And then we are also providing FIPS compliant images, and we support air gap workflow. I would highly recommend to use this depending on your policy requirements. With that, I hope you all give version 2.0 a try. We are very excited about it to give the benefits, and also happy to have feedback from your usage and continue to improve our product. Thank you. And if you have any questions, I'm happy to answer them.